Alright, welcome back guys. So we're going to finish up section 3.1 on probability. We had just got finished looking at using the multiplication rules to find the total possible ways this sequence of events can occur. So now we're going to look at types of probability, or the way, essentially the lens through which we can calculate or approach determining the probability of an event. Okay. All right. So, well, first of all, let's go over this bit of notation here. If you can see, we write. This is similar to the function of I said that backwards. The concept of a function. Okay. So any of you that have taken college algebra, this should make intuitive sense here. So. We write it like this. So capital E here denotes just some event that we're interested in finding its corresponding probability. And we write P of E to denote the probability of event E. Okay. So it's sort of like this is a probability function in a sense, and you plug a specific event into that function, and then it'll output whatever the probability of that event is. Okay, so we're going to be using this throughout this chapter anyway. And furthermore, when we express the probability of an event occurring, we can do it in three ways, guys. We can write a reduced fraction. We can write a decimal rounded to a certain number of decimal places. Typically, your homework will specify the number of decimal places. Or we can express it as a percentage, okay? Now, you want to be careful here. You never want to round down to zero. So, for example, if the event that, I don't know, a hurricane develops in the Gulf tomorrow, it might be something like this. The probability of that happening is 0.001, so 1 out of 1,000. You would not round this down to zero, because if you round it down to zero, what you're implying is that it would be impossible for that event to occur. So as long as there's some probability there, you cannot round this down to zero. In fact, this could be like you could have 1,000,000 zeros and then a 1. You still don't need to round it down to zero. Well, that's a little bit of an extreme example, but all right. So let's look at these three different approaches to probability. So the first one here, let me zoom in, is the classical, also known as the theoretical approach. Okay, and this approach is taken whenever each outcome in a sample space is equally likely to occur. So every single outcome, okay, an example of this would be like rolling a die or flipping a coin. Okay, we can treat finding the probabilities of events associated with those things using this theoretical approach. Okay, because each outcome is equally likely. Now, if we're, let me just stop there. Some other examples would include the lottery, bingo, drawing tokens from an urn, and then playing cards. Okay, so all the probabilities that are associated with all these different games of chance, guys, those are developed through this particular approach. Okay, and the way you find it, so let's say we have some event E, and we want to find the probability of E. The way you would determine it is you would determine the number of outcomes in this particular event, and then divide that by the total number of outcomes in a sample space. Okay, so an example would be if we're raffling off 50 tickets, okay, and you buy 3 of those, then the probability of you winning is going to be 3 out of 50. Okay, so 50 again would be the total number of outcomes. It's 50 because there's a total of 50 tickets. Or another example would be the probability of rolling a 12-sided die and it landing on 7 is 1 out of 12. 12 because there's 12 possible outcomes, and the numerator is 1 because only one of those outcomes comprises the event that you roll a 7. Okay, so 1 out of 12. You guys probably have some intuition already concerning this. All right, now let's look at the second approach. Empirical, also known as statistical probability. I've always really heard it called empirical. Okay, so this is basically, this approach is taken when you are trying to assign probability to an event by looking at how often that event has occurred in the past. So you're always looking in the past. So these are going to be based on observations. Okay, so again, from the past obtained from probability experiments. So the experiment is repeated until a pattern is formed. It's also based on collected data. Okay, so all the probabilities that are associated with disease and all the probabilities in the medical field, those are all based on past records, okay, or past data. So that would be an example of determining the probability of an event empirically. Here's another example. The probability that a voter is Republican in a particular county is 0.62. Okay, so the way this probability was determined was by looking at the past and looking at the percentage of Republicans versus Democrats and independents, whatever the case may be. And on average in the past is probably 62%. So then we can say that the probability that if you randomly select any given person from that county that they're going to be a Republican is 62%. All right, now this is interesting right here when it talks about the law of large numbers. Okay, so as an experiment is repeated over and over, the empirical probability of an event should approach the theoretical or the actual probability of the event. So this pertains more to like games of chance and things of that nature. So here's an example, the probability of tossing a head. So theoretically, we know that the probability of tossing a head is 1 out of 2. Because a coin has one head and there's 2 sides, right? So sample space consists of 2 outcomes, so 1 out of 2. Now you could also have determined the probability empirically by flipping a coin many times. And so that's what this graphic right here displays. What you have on the vertical axis is the actual proportion of those tosses that actually come up heads. And then what we have on the horizontal axis here is the number of tosses. So look what happens here, guys. Looks like maybe the very first toss, it comes up heads. Or maybe out of the first 2 tosses, 1 is heads and 1 is tails. Okay, so it's at 0.5. But then it kind of comes way up here and then dips way down. And that's, that can happen for sure. If I start tossing a coin and recording the number of times that I get heads out of those tosses, it could be that after the first 10 tosses, 7 are actually heads. But as the number of tosses increases, that number will start to kind of reach 50%, okay? And that's sort of what we see here, that as the number of tosses increases, the proportion of those tosses that are heads is actually, you can see it's now hovering around this horizontal line here, which is at 50%, okay? So if you were to ever try that, the more tosses, the closer that average is going to get to 50%, okay? And in theory, if you could toss a coin infinitely many times and look at the proportion that's heads, it would be exactly 50%. Now, experimentally, it's probably never going to be exactly 50%. It's probably going to be like, 50.05% or something like that. But anyway, let's look at this. I included this because I thought this was kind of interesting. So what we have here is just some different events and their associated probabilities. So being audited by the IRS, you have a 0.6% chance of being audited. Now, I will say that you can really only say this by saying for a random person selected, okay? So like if we're just selecting individuals in lower income class, then that probability might be different. But for any given random individual, the probability of being audited would be about 0.6%. Writing a New York Times bestseller. Now, notice this is not given, well, I don't know if this is a percentage and I just forgot to include that. I would think maybe it would be, because otherwise it's going to insinuate that any given person has a 0.5% chance of writing a New York Times bestseller. And I don't know that that's accurate. Probably what was done to determine this associated probability is they looked at the number of people that had written a New York Times bestseller out of the total population, and that gave us this decimal right here. And then winning an Academy Award, the probability of doing that's even less. And having your identity stolen, okay. Some people might be surprised that it's as low as it is. Spotting a UFO, so this appears to have the lowest probability here. All right, so anyway, so we've looked at classical or theoretical, empirical, and now we're going to look at the last one, which is subjective. This is the one you really want to stay away from because it's not scientific at all, guys. It's an intuition, educated guess, or an estimate, okay? So here's a couple examples. My property value has a 75% chance of increasing in value because the city is growing. So this figure is, in a sense, just made up. It's not really based on anything other than a person's intuition. Here's another example. The probability that my cat will run out of the house when the door is opened is 40%. Now, there could, a statistic like this could be obtained empirically. You could, every time you open the door, you could literally count the number of times your cat runs out, and then from that you could come up with a associated probability like this. But in most cases, if somebody were to say this, which I don't know that anyone actually does, this would be more subjective. Okay. All right, so now we're going to look at some examples of try to determine, whoops. Well, I seem to have disappeared. I don't know if you guys can see me or not, but anyway, it doesn't make any difference. Let's just continue here. So it says classify the statement as an example of classical, empirical, or subjective probability. Okay, so number one, the probability that a randomly selected number from 0 to 100 is divisible by 6 is 0.16. Okay. This is classical, guys, or theoretical, however you want to word it. Okay, because we can calculate the probability without doing any experimentation. And what happens is that there are 16 numbers that are divisible by 6 in this range right here. So we can say the total number of outcomes would be 16 out of the total numbers that could be generated would be 100. So 16 out of 100 is 0.06. So anyway, This is an example of classical, okay? Number 2, an analyst feels that a certain stock's probability of decreasing in price over the next week is 0.75. So anytime you see a word like this, feels, that should be an indication that this is subjective. And this is actually used a lot, this particular approach in investing. You know, some people will say, "Oh, I just had a feeling that this stock is really going to go up tomorrow, so I'm going to buy a bunch of shares." Number 3, according to a survey, the probability that a voting age citizen chosen at random is in favor of a skateboarding ban is about 0.63. So this would be empirical, because this would be based off of observations, or a survey, essentially, data, in other words. Okay, so I'm putting here empirical. All right. So now what we're going to do, guys, is kind of segue into actually calculating some probabilities. First of all, I want to go over this standard deck of cards. So, you know, most people have seen a standard deck of cards, but not everyone. I had a student, I think she was from South Korea quite a few years ago, but anyway, she was not familiar with any of this, so because of that, I've started including this. Anyway, let's just talk about it for a minute. Standard deck of cards, there are 52 cards, okay? There are 4 suits, and they're going to be hearts, diamonds, clubs, and spades. In fact, if you look right here, each of these columns is a suit, okay? Hearts and diamonds are going to be your red cards, and the clubs and spades are going to be your black cards. And then each suit will consist in this order of an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, queen, and king. The jack, queen, and king, guys, these are often referred to as face cards because they literally have faces on them. Okay, yeah, I just said that. Anyway. Hold on just a minute. I've got, let me show you. Get my notes right here. Here we go. This is actually probably what I should have put in there. I may end up changing these notes, but anyway. In this case, a suit is a horizontal row, but you can see what these cards look like. Over here, these are your face cards, okay? I think I'm going to keep this up because we'll refer to this, and I may actually try to put that in the notes. Anyway, let's get back to it. Okay, so that's a standard deck of playing cards. Okay, so we're going to try to find some probabilities. It says, assume that we have a standard deck of cards. What is the probability of drawing a 5 of hearts? Well, if you look right here, guys, 5s are in this column, and the 5 of hearts is right here, and there's only one. There's only one 5 of hearts, okay? So you could say that the probability of drawing a 5 of hearts, drawing a 5 of hearts is a simple event. It's comprised of just one outcome, this card, okay? So it's going to be 1 out of the total number of outcomes. Well, there's a total of 52 cards. So 1 out of 52, we're going to say. All right, what about number 2? What is the probability of drawing a club with a standard deck of cards? Well, a club is this whole row right here, guys. So there are a total of 13. Okay, each row or each suit has 13 cards in it. So there are 13 clubs essentially. So that event, drawing a club, is comprised of 13 outcomes because there's 13 clubs. So it's going to be 13 out of 52. Okay, 13 out of 52. And this, guys, is actually a fraction that can reduce. Believe it or not, these are both divisible by 13. So if we did that, we'd take it down to 1 out of 4. Also, I want to point out, I want to express this as a decimal. So, in case you're a little rusty, any fraction can be expressed as a decimal simply by dividing the numerator by the denominator. It would give us 0.25. Now, to convert a decimal to a percentage, you just multiply by 100. And so that would become 25%. Okay? So just pay attention to the homework. It'll tell you how it wants you to input these numerical values, whether as a fraction, a decimal, or percentage. It's usually done a fraction or decimal. Okay, number 3. The probability experiment consists of rolling a 12-sided die. So a die, remember, is singular for dice. So this is one that doesn't have 6 sides, but 12. So find the probability of each event. So event A, and this is the way we'll write it, guys, using that notation. The probability of event A occurring is equal to, and then we'll find that associated probability. And you've noticed, too, that all of these examples here, we are using the theoretical, classical approach to calculate these probabilities. So the probability of rolling a 2, well, there's only one 2 on a 12-sided die. See, it would go from 1, 2, 3, 4, 5, 6, all the way to 12. So 1 out of 12, because there are 12 sides. And let me express this as a decimal real quick, just so that you can see. 1 divided by 12 is 0.083333 forever. Okay, so I might just round this to 3 decimal places right here. All right, event B, probability of rolling an even number. Okay, well, you have to think, how many even numbers are there on a 12-sided die? Well, if they go from 1 to 12, then there would be 2, 4, 6, 8, 10, 12. Okay, 6. So probability of rolling an even number would be 6 out of 12, which is the same as 1/2, which is a decimal, is the same as 0.5. All right, event C, rolling at least, and apparently I did not write down the rest of this, so I'm going to make something up. Let's say the probability of rolling at least a 7. Okay. Okay, well, you have to fit at least a 7. So what does that mean? That means a 7 or bigger. So how many sides are going to be a 7 or bigger? Well, 7, 8, 9, 10, 11, 12. Okay, so it's 6 again. So the probability of C occurring is 6 out of 12, which is the same as 50%. Okay. Now, if it had said the probability of rolling a number greater than 7, then we would not have counted the 7. We would have started with 8. 8, 9, 10, 11, 12. So that would have been 5 out of 12. Okay. All right, let's go to number 4. Find the probability that a voter chosen at random is in the 45 to 65-year-old range. So we have to refer to this table right here, guys. Now what we would be doing here is taking the empirical approach. So what you're going to do is look and see how many actual millions of people are within this age group. Well, if you look over here, 45 to 64, there are 78.1 million. Okay, so the probability, sometimes you can write Well, I'll write it like this. The probability that a random voter is going to be in this age group, 45 to 64 years of age, is going to be equal to, well, there's 78.1 million people in that age group, okay? Now, our denominator is going to be the actual total number of voters, okay? So to find that, we have to actually sum up this last column. So I'm going to do that in the calculator here. Oops. Get it to stay. Okay, so just going to add up all the voters in each of these categories plus 53.9. And guys, you don't have to write like 53,900,000. You don't need to do that, because this is already understood to be in millions, okay? And the probability is going to be a ratio anyway, so the unit would end up canceling. Plus, and then there's 46 million that are 65 and over. Okay, so I hit enter, I'm going to get 226.9. And then lastly, what I would do is just divide those out. You don't want to try to reduce a fraction like this because it's got decimals in it. Okay, so let's carry this one out to 3 decimal places. So that 4 right here in the thousandths place is going to stay a 4. So this would be 0.344. That would be the probability. Okay. Anyway, there's lots of these types of problems where you're referring to data that's given to you in a table like this to determine the probability. Okay, let's keep going. All right, so some other important facts and knowledge that you need to know. I sort of already talked about some of this. The probability of an event occurring is always going to be between 0 and 1 inclusive. So inclusive means that we can include the 0 and the 1. Now you may be wondering, well, didn't you just say we couldn't have 0? Well, I said that if there is any sort of a probability there, you cannot round it down to 0. So 0 is perfectly fine for the probability of an event if there is no probability for that event occurring. Okay, so an example of this would be the probability that I pass this course, or excuse me, the probability of me both passing and failing this course would be 0. And the reason is because that event is impossible. You cannot both pass and fail the course. Those two events are what we're going to refer to later on as mutually exclusive. They both cannot occur at the same time. So anyway, and then again, well, not again, but in a similar vein, any event that has an associated probability of 1 is said to be certain to occur. Okay. All right, let's look at the second bullet. The sum of all outcomes in a sample space is always 1. Because what you've got going on here, guys, is to each of those outcomes there's an associated probability. And one or more of those outcomes is going to occur. So they all have to add up to 1, okay, for a sample space. I'll give you an example. Probability of flipping a heads is 0.5. The probability of flipping a tails is also 0.5, because when you flip a coin, one of those two events is going to occur. All right, so let's look at this this continuum here. All right, so like I said, if an event has a probability of 0, that means it's impossible. And then anything with a probability of 1 is said to be certain to occur. And then 0.5 means there's an even chance, like flipping a coin, and then anything around 0.75 or 75% is said to be likely. Anything around 0.25 or 25% is said to be unlikely. And then, similar to what we saw in chapter 2, we use this term unusual again, okay? So if an event has an associated probability that is less than or equal to 0.05 or 5%, in other words, we say that that's unusual. And an unusual event is highly unlikely to occur. So you remember from, let's see, I guess it was 2.4 when we were talking about standard deviation. The empirical rule said that within two standard deviations, we have 95% of the data of a distribution. So we said that anything outside of that was unusual. So this is essentially stating the same thing, just in probabilistic terms. All right, and then the last term that we're going to learn is complement, okay? This is not like a compliment that you give someone, to make them feel better about themselves, or maybe they just deserve it, or both. A complement of an event is, if you look here, the set of all outcomes in the sample space that is not included in the event. Okay, so looking at this Venn diagram right here, this square, guys, represents the sample space. So all the different outcomes that could occur. If you remember, an event is a subset, so here is the event, okay? So all of the outcomes that don't comprise the event, they're on the outside, and this is what we refer to as the complement of E. Okay. And it's denoted E prime with this little apostrophe. Okay, it's read E prime. And so typically it's written something like this: the probability that E prime occurs is equal to whatever, okay? Or you could also read it, the probability of the complement of E. Another way to think about this, guys, is the probability that E does not occur. That's what the complement is. It's the probability that that event E does not occur, okay? And then this rule right here, this goes back to this bullet point right here, that the sum of all outcomes in the sample space has to be 1. Well, then it stands to reason that the probability that the event will occur plus the probability that it does not occur should be equal to 1. So let me give you an example. The probability that it rains tomorrow is 20%. Okay, so the event is that it rains tomorrow. The complement of that event would be that it does not rain. So intuitively, you know that if the probability that it rains is 20%, that must mean that the probability that it does not rain has got to be 80%. And together, they make up 100%, right? Because tomorrow it's either going to rain or it's not going to rain. Now, you may be wondering, why are we introducing this idea of a complement? Well, because it turns out that when you're trying to find the probability of some events, it's actually easier to figure out what's the probability that they do not occur. And if you know that, then you can find the probability that they do occur, because you know that together they have to add up to 1, or 100%, in other words. Okay, well, let's look at some examples here. So example A, it says, if the probability that E occurs is 5/9, what is the probability of E complement, or E prime? In other words, what's the probability that E does not occur? Well, one way you could think about this, guys, is that, okay, thinking back to that equation, the probability of E plus the probability of E complement has to equal 1. Well, if we know the probability of E, it's 5/9, and we don't know the probability of E prime. If you were in algebra class and I replace this probability of E complement with an X, you would know that you have to subtract 5/9 from both sides of this equation. So this implies that the probability that E does not occur is going to be equal to 1 minus 5/9, which is 4/9, okay? And so like I said, if you know one or the other, you can find the probability of the other one just by subtracting it from 1. So for example, if I had known that the probability that E does not occur is 4/9, then I could subtract that from 1, and that would give me 5/9, which would be the probability that E does occur. And we'll see an example here in just a minute in which we utilize the complement. Okay, example 9. Probability of A prime, or in other words, probability that A does not occur is 92%. What is the probability that A does occur? Well, 100% minus 92% is 8%. Okay, so the probability that A does occur is equal to 8%. And I kept this as a percentage because this probability in the problem is given to us as a percentage. All right, let's go to example 10. This video may be just a little bit longer than average, but I didn't want to have to do another part 3, okay, because you guys probably get tired of. And one of the reasons I used to just, my videos, they would just be one long lecture, but because of some of the professional development that we have to do, we are encouraged to make shorter videos. Although I'm not sure why it really matters, because you guys can just pause these and take a break. But anyway, example 10, it says find the probability that a voter chosen at random is not in the 18 to 29-year-old range. Okay, so this is an example in which we can implement that idea of a complement. Okay, so what we could do is, so the probability that a random voter is not within this range would essentially be the same as asking the probability that a random voter is within this range, or this range, okay? One of these three. So it's actually easier to say, okay, well, if the probability that a voter is within that range plus the probability that the voter is not within that age range has to equal 1, then I can figure out it's easier for me to figure out the probability. I just need to know one of these two things here, right? Because once I know one of these numbers, I can subtract it from 1, and that'll give me the probability of the other event. So it's actually easier for me to calculate the probability that the voter is within this range. Okay, 18 to 29, so that would be 48.9. I'll put this over here. It would be 48.9 divided by the total frequency again, right? So I'm just going to, this is the same chart from above, guys, so I'm just going to borrow this total, 226.9 million. Okay, let's see what this decimal is. Now, in instances like this, you might actually want to round the decimal to 4 decimal places. You only want to round it to maybe 3 at the very end. Okay. The reason you want to keep it as long as possible during the process is so that you're not sacrificing accuracy. So anyway, let's see what this ratio is. Okay. So I'm going to round this to 4 decimal places, so 0.2155. Okay. So this, let's see if I can put this, is the probability that this event occurs. So then we can utilize that idea of a complement. So 1 minus this probability will give us the probability, I'm going to write it this way, so the probability that a voter is not within that age range is going to be equal to 1 minus the probability that the voter is within that age range, okay? And so this would be 1 minus 0.2155, and, well, I think I know it, but I don't want to. Now, I would round this to 3 decimal places now, okay, because this was my very last operation, so 0.78. Well, I'll just write the whole thing out first, okay, which would round to 0.785. So this would be the probability that a voter is not in that age range. In other words, what this is saying is that the probability that a randomly selected voter is 30 or older is 78.5%. Okay. All right. I think we got 3 left. None of these are all that long, though. Okay, example 11. A probability experiment consists of rolling a 6-sided die and then spinning this spinner right here. So what is the probability of event A? So event A would be rolling a 5 and the spinner landing on green. Okay. So probability of A. Well, we can take a theoretical approach to this. There's only one way that you can roll a 5 and have the spinner land on green, okay? So the number of outcomes that comprise this event A is just 1. Now what we need to do now is see how many total outcomes are possible. And this is where we use that multiplication rule. So multiplication, I'll just abbreviate, rule, okay? It says it's the total number of ways that event 1 can occur, which would be rolling a 6-sided die. Well, there's 6 total outcomes. So it'd be 6 times, and then this spinner has 4 different colors, so there's 4 outcomes there. So 6 times 4, okay, which is 24. So that means the probability of event A, which is these 2 things occurring in sequence, is going to be 1 out of 24. Okay. All right. Let's go to number 12. So it says the access code consists of a letter followed by 4 digits. Any letter can be used. The first digit cannot be 0, and the last digit must be even. Find the number of possible access codes. So what they're doing here, guys, through parts A, B, and C is kind of taking us through this step by step. Because again, we're going to take the classical or theoretical approach. We can figure out the total number of access codes, and that's going to be the total number of outcomes, or the size of our sample space. Okay, and so for this, we're going to use the multiplication rule again. Okay, so if it's a letter followed by 4 digits and it says any letter can be used, well, that means there's 26 possibilities times. And then for the first digit, it says we cannot use 0. Well, that means there's 9 left that we can use. So there's 9 possible ways we can find a first digit. And then it doesn't specify anything about the second and third digit. So we assume they can be any one of the 10 digits, 0 through 9. So there's 10 digits available, and then another 10 digits available. And then it says the last digit must be even. So we have to figure out how many digits are even between 0 and 9. Well, 0 is even, guys. So we've got 0, 2, 4, 6, 8. So we've got 5. Okay, and so if we multiply all these will be the total number of access codes. 26 times 9 times, I could just do the 2 tens as 100, and then times 5. And we're going to get 117,000 possible access codes. Alright, so that's probably going to be our denominator in any of these probabilities that we try to calculate. Okay, so it says, what is the probability of randomly selecting the correct access code on the first try? Well, that means you get it right the first time, and there's only one way to do that, okay? So the probability of, I'm just going to say, being correct in guessing that access code is going to be equal to 1 out of 117,000, which is, let's look at this as a decimal, okay? 1 divided by 117,000. Okay, this is what I wanted you to see. This right here, guys, is scientific notation. So what this is 8.547, etc., times e to the negative 6. So that what that negative 6 does is basically move this decimal to the left 6 places. So if I were to do that, I would then have 5 zeros between the decimal and the 8, okay, because the decimal was right here. So we move it to the left 6 places, and I'm going to carry out the 547, okay, 547. So you may see one like this in your homework. So pay attention to the number of decimal places it tells you. I might just round this to maybe 9, okay, or 85, something like that. But anyway, you can see the probability for that event occurring is extremely low, as you would imagine. If there's over 100,000 possible access codes and you're going to try to guess correctly, you've got a very low probability of doing that. Now notice there is some probability here. That's why we don't round down to 0, because 0 would say that that event is impossible. And we know it's not impossible, it's just extremely unlikely. All right, what about part C? What is the probability of not selecting the correct access code on the first try? Well, guys, now is when we're going to use that idea of a complement. So on the first try, 2 things are going to happen. You're either going to be right or you're going to be wrong. So the probability of being correct plus the probability of being wrong has to equal 1, okay? We know what the probability of being correct is. It's 1 out of 117,000 plus the probability of being wrong has to equal 1. So anyway, you're just going to subtract the probability of being correct from the 1, okay? So the probability of being wrong or not selecting the correct access code in your first try is going to be 1 minus 1 over 117,000. All right. Guys, I could just subtract this from 1, and that's probably, well, in fact, I already got this number in the calculator, so I can just say 1 minus, and to tell the calculator to use this previous value, you go to second and the negative key, because see that answer up there? To plug in that previous number. All right, so let's look at this. 0 point, we've got a bunch of 9s, don't we? In fact, we've got 5 of them. And that's where I'm going to leave it. 3 decimal places would be something like this. And if you notice, this number is really close to 1. But we don't round it to 1 because we know that, so this is the probability of being incorrect on the first guess, which makes sense. If there's over 100,000 different ways or different access codes possible, you're almost guaranteed to be wrong if you're just guessing, right? But notice, it is still possible that you could be right, and that's why this is not 1. All right, well, let's do one last one here. So, example 13, it says a couple plans to have 3 children. Each child is equally likely to be either a boy or a girl. So using a tree diagram, find the probability that exactly 1 child is a girl. Okay. All right, so I included this one because you guys needed to see a tree diagram. Okay. So there are 3 children possible. Let's say first child, second child, and third child. Now, each of these children can be, well, hold on a minute. No, let me not quite do it like this. Just change this up. Now let's do it like this. Okay, so the first child can either be a boy or a girl. Move this down. Okay. Now, the second child can either be a boy or a girl, but you have to take into consideration the first child. So if the first child was a boy, then the second child can also be either a boy or a girl. And then if the first child was a girl, the second child can still be either a boy or a girl. Okay? And then we do this one last time for the third child. So you're basically working at the ends of these branches. That's why we call this a tree diagram. At the end of each branch, the possibilities are either a boy or a girl. Okay, so if the first child was a boy, the second child was a boy, then the third child can still be either a boy or a girl. And then if the first child was a boy, the second child was a girl, then the third child can either be a boy or a girl. And then the same thing. If the first child was a girl and the second child was a boy, then the third child can either be a boy or a girl. And then finally, if the first child was a girl, the second child was a girl, then the third child can be either a boy or a girl. So now let's look at all of our possibilities. So the first one could be a boy, the second one could be a boy, and the third one could be a boy. So boy, boy, boy. Basically what you're doing now is you're running down each possible branch sequence. So if the first one was a boy, the second one was a boy, and then the third one was a girl. So that would give us a boy, boy, girl possibility or outcome. And then if the first one was a boy, the second one was a girl, then the third one was a boy, then you would have this combination of boy, girl, boy. And then very similarly, a boy, girl, girl. Okay. And so you just, basically you're starting right here. You're just going down every possible route, okay, through this tree. And then if the first one was a girl, the second one was a boy, and the third one was a boy, then you've got a girl, boy, boy possibility. And then similarly here, you got a girl, boy, girl. I know this is a bit tedious, guys, but it's done more for understanding than just an exercise in tedium. And then finally, you could have a girl, girl, boy, or all three could be boys. Okay? So that's when you, so you know, if a couple has 3 kids, these are all the possible outcomes. Okay, there's 8 of them, and that's why it's kind of rare to see a couple with exactly 3 boys or 3 girls, because that can only occur one way. But we want to find the probability that exactly one child is a girl. So we need to count up the number of outcomes that include having just one girl. Well, this one, this one, and just looking around here. Well, oh wait, there's one more. This one, 1 girl and 2 boys, and I think that's about it. What I'm seeing. So, see, basically the 3rd child could have been a girl, or the 2nd child could have been a girl, or the 1st child could have been a girl, and then the others of course have to be boys. So we can say that the probability that you have exactly 1 girl is equal to 3 out of 8, because there's 8 total outcomes, and 3 of those involve having exactly 1 girl. Okay. Alright guys, well I know this was a little longer video, but go ahead and get into some of that homework and try some of these out. Let me know if you have any questions, okay? I can meet you in Zoom or whatever to help you out, but you gotta let me know. Anyway, you know, a lot of this stuff takes practice, okay? So don't get discouraged if you're not, you know, great at it initially. It just takes, like I said, repetition, and through that repetition, then you really start to kind of understand what it is you're doing. Okay? All right, well, I'll see you in section 3.2.